For those who have not met me, I'm David Couzens. I chair the Professional Standards Board here in the Society, and I've been an aerospace engineer for over 35 years. In that time, I sort of mastered something about fixed-wing aeroplanes, had a short encounter with helicopters, and was totally confused by the concept of ornithopters. Anybody who can make the link between combining lift and thrust in something that flaps must be rather exceptional in their creativity and their engineering skills. And hopefully we'll hear tonight somebody who's achieved just that. And I suppose, like most of you, to me the concept of a flapping flight goes back to the days of the legends of Icarus and Daedalus, the fantastic inventions sketched out by Leonardo in his various works, those grainy films of intrepid inventors building contraptions of very lightweight structures with silk and feathers and a number of other things, and then the works of Heath Robinson. But actually seeing something that works has so far certainly eluded me. The work we're going to hear about tonight, that Professor James DeLaurier has been engaged upon, I suspect started from that same sort of curiosity. How on earth is this thing going to actually happen? So alongside a mainstream career, both academic and industry-based in aerospace, James progressively moved forward with the concept of the ornithopter. I won't go through his CV. He's got far more interesting things to talk to us tonight about that. Except I noted in the flyer for the lecture, it said that the aircraft first took the runway in 1996 and achieved successful flight in 2006. It sounds like some of our airports today when you sit in the queue. But I'm sure in those 10 years a huge amount of effort and engineering went on. So without further ado, James, the floor is yours.
I wish to thank the audience for coming on such short notice. It's my pleasure to be here. I had promised myself years ago that when the aircraft flew, I was going to come to my favorite aeronautical place on earth, 4 Hamilton Place, and present a lecture to my fellow members. This is actually my 3rd lecture. My previous 2 lectures in the past have been on lighter than air technology. There's a lot of advantages to that because once you've paid for the helium, you're off the ground. And then everything else is details. Not so with an ornithopter. Rising from the ground has been the major challenge. All right. You notice I'm a professor emeritus now. That's essentially Latin for old professor. But I still maintain a research group, and I'm still doing research on flapping flight. I hadn't realized that what started out as a hobby would actually become a interesting research topic with applications to micro-air vehicles. Yesterday, I was at Queen Mary University of London. As you know, they had their 100th anniversary conference, 100th anniversary of the Aeronautical Department. And I had the honor of being asked to be one of the speakers. And I talked about small-scale flapping wing flight as applied to micro-air vehicles, and also some research, current research we're doing on the way a flapping wing changes shape for efficient flight for an animal like a bird or a bat. By changing shape, I mean the way they bend in and go out on the stroke. I do this a lot. But tonight I want to talk just about the big flapper. That's what we call it, the large ornithopter, which definitely does not bend its wing. At least, you don't want it to. If it does, you're in trouble. Here's a picture I particularly like. This is Dusk, and the aircraft was wheeled out. This was in 1997. And it shows how unsubstantial an aircraft has to be lightweight. And the structure is an interesting mix of traditional and non-traditional. The fuselage looks pretty normal for an ultralight type of aircraft. It's aluminum tubing. The vertical tail is made out of wood. The wings are made out of carbon fiber and Kevlar. There are appropriate materials depending on the loads that are imposed upon the structure. And sometimes wood is a lot better than carbon fiber for certain types of application, and the same with aluminum tubing. People have asked, well, why didn't you use like a carbon fiber shell for the fuselage? It makes it real streamlined. Well, that's a one-way street, actually. We're operating on a very small budget, and space frame structure can be very light and stiff and strong and easy to repair, which is important, and easy to modify. So that was appropriate for an experimental aircraft. People keep asking me, am I inspired by Leonardo da Vinci? Well, in the sense that I admire Leonardo da Vinci, and I feel humbled by his accomplishments. I mean, not only did he work on ornithopters, but he painted the Mona Lisa. So, yes, in that sense I'm inspired, but the aircraft doesn't draw on da Vinci's solutions for flapping flight. We sort of took a fresh sheet of paper, actually, and came up with our own solution. As far as I know, and I haven't ever found any different throughout the years, this really is the world's first successful ornithopter. Alphonse Penaud's rubber band powered flapping model. Its wingspan is only about 30 centimeters. But it set the template. It's the template for all model ornithopters for many years afterwards. So if you're going to buy an ornithopter of your own, what you would do is you go to a science store, or maybe the gift shop at the Science Museum, and you'd buy these plastic ornithopters made in France. They have a little rubber band. They're called Tim birds. And the Tim birds really don't differ in fundamental principle to this aircraft, just in the material. All right, let's look at past ornithopters, particularly admirable human-carrying ornithopters by Alexander Lippisch. I suppose this is the one place where I don't have to say who Alexander Lippisch is or what he had done, but just for completeness, of course, he is a pioneering aircraft designer who developed tailless aircraft, later on in his life, wingless aircraft, ground effect aircraft. I think they're called WIG now, wing in ground effect type aircraft. But he also had a lifelong interest in ornithopters, and I always found that encouraging because even though ornithopters became marginalized after the discoveries of Sir George Cayley about separating thrust from lift, some people still maintain an interest in exploring the possibilities of mechanical flapping wing flight. For the most part, these were characters who were a bit hapless in their approach. It had been mentioned about the grainy black and white film footage of people with wings strapped to their arms jumping off a bridge, or some sort of a contrivance that's going down a ramp and then it hits the ground, doesn't fly. Something that was slowly going down a street for some reason, flapping its wings, but just creeping along, slower than you could ride on a bicycle. And usually there's funny music being played too. And I really did not want to add to that body of foolish flapping footage. Okay, so that was something that we wanted to avoid. With lighter than air technology, working on blimps and airships, I must tell you quite frankly, there's a certain what they call giggle factor. You meet somebody and say, "Oh, I design blimps." Oh, okay. Imagine saying, "Oh, I design ornithopters." At that point, they sort of back away, say, "Oh, okay." But Alexander Lippisch was a very respectable individual, and what he did is he built had this human-powered ornithopter built and tested it in the late 1920s. And in a time-honored tradition of professors, he used students to pull it into the air and to act as the prime mover of the aircraft. In his paper, published by the Aeronautical Journal many years later, he talked about one student who was particularly good at this. His name was Hans. And on a Friday afternoon, Hans asked permission if he could have the weekend off. He wanted to go visit his girlfriend in a neighboring town. And Lippisch said, "You may, if you can make this aircraft go further than you ever have before." So Hans being a young man and appropriately motivated, did so. So sometimes I refer to this as the world's first hormone-powered ornithopter. Just a thought. Now, in England, there's the Hartman Ornithopter in 1959. Hartman was an architect, and you see that he's really trying to imitate bird wings, which doesn't show a great deal of understanding about the principles of flapping flight. But I admire this work anyway, because he clearly shows that an ornithopter doesn't have to slavishly imitate a bird in all particulars. The fuselage looks like it's from an ultralight aircraft, as is the tail group. In this case, it was towed behind a car, towed into the air, and then it was released. Both this ornithopter, as well as Lippisch's ornithopter, never achieved sustained flight. They were like powered glides. In Lippisch's case, it would glide further with the wings flapping than without the wings flapping, so Lippisch felt he was proving what he had to prove. All right, let's talk about some other interesting designs. This is the ornithopter suit, okay? And here's the pilot. Now, believe it or not, the undercarriage stayed attached. So here's the undercarriage, which is attached to the whole apparatus. This individual had a canard hat. You see the canard hat? There it is. So pitch control was from operating his head. All right. I don't think this ever got built, and if it did, I don't think it flew. But the canard hat was an intriguing idea. Imagine if you were flying and you were trying to nod to somebody on the ground. You'd go into, obviously, a fugoid oscillation. So that's one attempt. Here's the chicken plane. Why a chicken? They don't even fly. I don't know. And to hedge their bets, they also had a propeller on the beak. You see the pilot here. Now look closely. Here's the co-pilot, and over here is the flight engineer. So this is the sort of thing that, the kind of baggage, you could say, that comes along with flapping wing research. Actually, it was more so in the past when we first started than now, because it's becoming a mainstream research topic, actually. Okay. This slide shows my daughter April holding her pet bat. Pet bat's name was Cassandra. The bat lived for many, many years. And April used to take the bat out and fly it in her bedroom, and I really enjoyed watching it because it flew so beautifully, so gracefully, and would never like hit anything. It would just do circles, do laps. The thing is, Cassandra has a message for us. The message is that creatures can have a membrane wing and still fly successfully and fly well. There's a lot of hocus pocus about feathers, the role that feathers play for birds' wings. You'll read these articles that in all seriousness will tell you that the feathers valve, they valve on the upstroke and close on the downstroke, not really looking at the fact that the feathers overlap in the wrong direction for that. Or maybe there's something about tip flick on the feathers, or the feathers are sensing boundary layers. The fact of the matter is this is a mammal's solution to flapping flight. And it works efficiently and well at a size range comparable to that for birds. There's tiny bats about the size of hummingbirds, and there's large bats that are, the size of seagulls or bigger. I don't know if very many people know about bats. It's a rare occasion to actually live with a bat, but they're not flying mice. They're actually very intelligent creatures, about the intelligence of a ferret. They live for a long time, 2 or 3 decades. They sleep most of the time. They only wake up to eat and reproduce. Like I said, they're very smart creatures. Okay, let's talk about the forces on an airfoil. Most of you who've been educated in aerodynamics know the traditional lift and drag representation. You have to do it a little bit different if you're looking at flapping flight. In this case, you have to deal with what's called the normal force that's perpendicular to the chord of the wing, and the chordwise force, which includes camber drag and friction drag. And you have to have deal with a force called the leading edge suction. Leading edge suction is very important for our solution to flapping flight. Also, you'll notice here, this C denotes that's the force from circulation, but we also account for separated flow. So this would be the normal force from separated flow, and this is the force from apparent mass. It goes on, but in point of fact, the analytical model and the development of the ornithopter, the small-scale ornithopter, and its actual testing is documented in 3 papers in the Aeronautical Journal back in the mid-1990s. Now, if you look at birds flying in a wind tunnel, which I have, there's a lot of things going on with the kinematics of the wings. We hypothesize that the main motions that give rise to what we want is the plunging motion, up and down here, and the pitching motion, which is theta. And all the other things like wing folding or fore and aft motion of the wings, we concluded that these were of secondary importance. In fact, might even be aeroelastic artifacts from the flapping. All right, let's talk a little bit about leading edge suction. I guess most people here really know what this is, but just to go through it for completeness, here's a streamline pattern. Here's the stagnation point. Ahead of the stagnation point, the flow actually goes forward for a short distance along the airfoil and then makes a rapid U-turn. From Bernoulli's equation, of course, you have a low pressure region because of that. And this denotes a typical pressure distribution around the nose of an airfoil. And of course, this is assuming that there's no local separation or laminar separation bubbles. This is for a properly shaped airfoil at a high enough Reynolds number that this happens. Which points out something right now, that the solution for flapping flight I'm describing here tonight is for larger scale ornithopters. It makes no sense at all for small scale ornithopters. There are other solutions that work well at that scale. Okay. Very important part of this was aeroelastic tailoring. Aeroelastic tailoring has some specific meanings for aircraft design, but this is a somewhat different but analogous meaning for ornithopters. The main structural element is the leading edge spar. By leading edge spar, I really mean leading edge. This is it with regard to the resistance to bending and twisting of the aircraft's wing. The ribs are rigidly attached to this spar, okay? Now the reason we do this is because the centers of pressure are aft of the spar, so in the course of flapping the wing up and down, these centers of pressure will act about the elastic axis to give twist. So the flapping is imposed, but the twisting is an aeroelastic response. Okay, having said that, you'd better be really sure that you get the right distribution of twisting compliance built into the spar ahead of time, because you'll have no control after that. If you have a wing that's too loose, if the spar is too compliant, you'll actually take energy out of the flow and, well, you won't fly. If you have a spar that's too stiff in torsion, you'll be having massive separation in the course of the flapping, and you won't have any thrust. So you have to get it just right. And that had to be done theoretically. So a theoretical model was developed over several years to predict the behavior of this type of flapping wing. The airfoil is very special. This was designed for us by Professor Michael Selig of the University of Illinois. He did it as a favor. I was at a conference at the University of Notre Dame in 1987. I gave a presentation on our work on the ornithopter up to that point for the small-scale ornithopter, and we were trying to use single-surface airfoils with faired leading edges, and they were just miserable. They were awful. And he said, well, I can design a special airfoil for you if you're interested. And I said, sure, I am. So he did. And the thing is, there's 3 very special things about the airfoil. First of all, there's no specific ideal angle of attack, which makes this different than a lot of other airfoils. Its goodness is actually smoothed over so that it's not real good at one particular angle of attack, but it's pretty good over a wide range of angles of attack, which is important for an ornithopter because you have to you have to go through quite an excursion of angles of attack during the flapping motion. The second thing is, I told him I wanted some structural depth, because if I have to have the spar right at the leading edge, I can't have this too skinny. I need sufficient depth for the shear web and the spar caps to give me the requisite amount of stiffness and strength. And the third thing is, I can't use a laminar flow airfoil or anything like it. I can't use one of these specialty airfoils that you have to build to micro precision, because the way it was constructed, you know, with fabric covering ribs, there's going to be imperfections, there's going to be little discontinuities. So it has to be forgiving. He came up with all three of these. Here's an actual wind tunnel test, results from that on an airfoil, at a much lower Reynolds number, actually, than we were flying at. The way to look upon this is for positive angles of attack. This is for negative angles of attack. This would be the underside from the leading edge to the trailing edge. You see the flow is completely attached until you get to about minus 7 degrees, and then everything takes off at minus 8 degrees negative angle of attack. Look at this positive angle of attack. This was more important because we fly at, at a positive angle of attack. This is holding on really well, and nothing is fully separated all the way to 15 degrees. Now this is really gets me for a thick airfoil at that Reynolds numbers. Okay, but this was from actual experiment, flow visualization experiment, and the behavior of the ornithopter also confirms that that was in fact true. Okay, so we have a thick airfoil. How do we make the thing twist? All right, that's the next step. So that was one of the key inventions for the project. And we do this by means of a method, a structural design we call shear flexing. Shear flexing means essentially you cut the trailing edge, so you're opening up the torque box. Let me explain that in an analogous fashion. Let's say you have a paper tube. You try to twist it. It's resisting the twisting, right? Okay, take your knife, put a slit down the length of it. All of a sudden, it's very compliant. Okay, look at the end of the paper tube. Imagine the circle morphs to an airfoil where the slit remains at the trailing edge. So that's the idea. We open the trailing edge, and the torsional compliance goes way down and is dictated primarily by the torsion of the torsional characteristics of the spar itself. We want to keep the trailing edge from splitting apart this way, so we have these sliding clips to sort of hold it together. And that was good enough for a patent, actually. It has other applications like variable pitch rotors. You can drive this. It doesn't have to be passive. You grab the trailing edge pieces and move one way and one the other way. You can induce a warp, a twist in a thick wing. We actually demonstrated that with a radio-controlled model. Okay, so here's what the model ornithopter wing looked like. And this came as the result of numerous computer experimentations. So we didn't have an optimization program as such. We were just taking one design and improving on it and tweaking it and finally coming up with a viable solution that would produce the lift and thrust we needed. But the main features are, first of all, it has a cranked spar. The crank is there in order to bring the centers of pressure of the outer portion further aft, which then increases their distance, this lever arm distance, from the inner part of the spar. In other words, it enhances the twisting on the inner part. If we had a straight spar, we'd have to make this too weak, too small a cross-section to get the linear twist we wanted. By putting the crank in here, we could make this spar a lot more robust, which is where, of course, the maximum bending moments are. Other things that we learned are that the fabric, everything aft to the spar, has to be as absolutely light as possible. The reason being, and you can easily visualize this, is that the most efficient flapping is about 90 degrees out of phase, where the pitching is lagging the plunging. But if you have mass back there, it drives at 180 degrees out of phase. So you really have to keep the mass to a minimum. And Cassandra the bat also had another contribution, this thing we call the bat tip. In order to get a completely linear twist, dynamic twist during the flapping, we would have had to have brought the cross-section of this down to 0. And that's, well, weak. You know, that would be a weak spar and be difficult to incorporate. So this little piece out here, which was inspired by the shape of a bat's wing near the tip, gave us the extra little twist we needed to allow us to keep a finite thickness on the leading edge spar. Okay, the wing cross section, they are just sliced from insulating foam. We tried different types of foam, some exotic foams from Germany. We found just the foam we could buy at Home Depot. The insulating foam was actually overall the best, which is good because that saved us money. 1/8 inch thick and capped with spruce strips. The trailing edge are 2 carbon fiber strips. Here's the wing spar. This is the shear web and a foam core and covered with Kevlar and epoxy layers. And of course we varied the orientation of the fabric to tailor the GJ, the torsional compliance, and the well, so the shear web was backed with carbon fiber to give us a requisite bending stiffness and strength. Okay, here's the model. This is nominally the quarter scale proof of concept model, and which led to the big Ornithopter. Here's the engine and the drivetrain, and the center section went up and down on a Scotch yoke type drive. I like these old drives. I mean, no matter how clever you are with the mechanism, it turns out some old Scotsman invented it in the 18th century. It always seems to work that way. Anyway, this is called the Scotch yoke. Notice that we have a center section that goes up and down, and then we have outer panels that are pivoted on these links, these vertical links. This was Jerry Harris's invention, who was my research partner in this. He was an engineer at Battelle Memorial Institute in Columbus, Ohio. That means that when part of the wing is going up, other parts are going down. And that helps to balance out the unbalanced force that would be felt at the fuselage. At all times, we were thinking in terms of a full-scale ornithopter, so we were thinking about the comfort aspects for a pilot. The other thing, too, which is good about this 3-panel design, which Jerry incidentally had obtained a patent on, is that it evens out the power stroke. You size the engine for an ornithopter in accordance with the peak power required. For a propeller-driven airplane, the average power is the same as the instantaneous power through the whole cycle of the propeller going around. Not so with an ornithopter. The peak power is usually the downstroke, and then the upstroke is a lot less power. Well, if you design according to the peak power, you're going to be putting in too large of an engine. So you want a certain amount of energy storage, and you want to balance out the force required. The pterosaur built remotely controlled pterosaur built by the AeroVironment Corporation in the 80s used bungee cords along the neck. So on the upstroke, it stretched the bungee cords and stored that energy, and then that energy was used for the downstroke. We do it different. Here's the section cycle history. The thing that's nice about this kind of wing is that it's thrusting both on the upstroke and on the downstroke. Of course, more so on the downstroke, but it is definitely thrusting on the upstroke. This makes this wing much more efficient, much higher propulsive efficiency than is the case, say, for a membrane wing ornithopter, like the one like the Penaud design I showed you earlier, an ornithopter with no leading edge suction. Our propulsive efficiency for the model was 50%. Now, that doesn't sound very exciting, I'm sure, because you can make propellers at that Reynolds number, 89% or higher. But in fact, you have to remember that an ornithopter wing also lifts as well as thrusts. And so it has an induced drag associated with it. So if you subtract the induced drag, all of a sudden for this model, the propulsive efficiency was 89%. For the big ornithopter, the big flapper, it's even more so. So it's a very efficient way of achieving flapping wing propulsion. Here's the completed model hanging in my lab. It had a long development period with various wing shapes before this. The earliest wing shapes we tried were just simply cut and try. When the scope of the problem became evident, that's when we started applying more and more analysis of wind tunnel testing to it. And it took years until we reached the point where we had successful flight. That's why the wings look nice and new, but the fuselage looks kind of beat up because the Ornithopter, well, got beat up a lot. It was made numerous unscheduled landings in the course of our testing. Okay, I want to show a video of this. Okay, now back to what this led to. We built actually another model, which was slightly bigger. It was meant to be hung at the Canadian Pavilion at Expo, but we had no reason to fly it because everything we had to learn, we learned from the previous model. But we did manage to wind tunnel test it at the National Research Council 9-meter subsonic wind tunnel. They gave us 2 weeks of priceless time in that wind tunnel to obtain the characteristics because now we're going for the full-scale design. And we really had to quantify this information. Okay, here's the construction. It was built in my lab, and my lab seems big until you're building an aircraft in it. And it was like pretty crowded, you know, trying to build a full-scale aircraft. This is the wooden vertical tail I mentioned. Here's the horizontal tail. It's a stabilator. The whole thing moved. That was the only thing that made sense for this ornithopter. And here's the metal truss work of the fuselage. And here's more about the fuselage construction. This is aluminum back here. The central portion, which we call the thorax, that's the one thing about working on innovative aircraft. You get to name the parts. So this is the thorax. And this fuselage area, the cockpit area, was again aluminum. Now let me show you the wing construction. It's somewhat like it was for the quarter scale model, but with some differences. First of all, we had to have this jig. We have a plywood. This is the plywood shear web that's faced on the other side with Kevlar and epoxy at 45 degrees. The cap strips are these carbon fiber units that you see here. These ribs were laser cut for us by a British company called TEW Engineering, T-E-W. They did a really great job. And then in between these ribs, we had these foam blocks that are roughly cut out. And once they're glued in and the glue is set, we can use a bar sander to sand the foam down to shape, using these ribs as a guide. Now what really worked out well is the laser cutting leaves kind of a charred surface. And if you start seeing the char disappearing, you stop sanding. That worked out well. And we had a carbon fiber piece in the leading edge. Okay, that's the first step. Next step is we had to cover it with epoxy impregnated Kevlar. And It took a while to find the appropriate epoxy. What we used was West Systems epoxy. What I did is I called my friend Ray Morgan at AeroVironment and said, you know, we were doing some test spars on the epoxy we have. This isn't working well. What do you suggest? And he told me that, and that's what we use. Notice that we wet the surface, and then it's put down. There's 5 layers of different orientations to give the requisite torsional compliance along the length of the spar. All this was determined by theory. But we had confidence in the theory based on the flight of the quarter scale model. Okay, here's the completed wing structure. It's green here because it has this ultraviolet protective paint on it, used for boats actually. Here are the ribs. They just look like bigger scale versions of the quarter scale model. They're foam, again the blue foam, only this time it's like they're 1/2 inch thick. And they're capped with spruce strips. Again, that's an idea I got from AeroVironment that Ray Morgan told me about. It actually works out better than using carbon fiber as cap strips on the ribs, because carbon fiber, if you have the sufficient strength, it'll still be thin enough that it might not have the sufficient stiffness to locally tear away and buckle from the foam. I mean, there's not much grabbing on the foam. You know, the foam will just tear easily. But the wood itself has its own structural buckling integrity that would help prevent that from happening. So wood is what we used. Incidentally, for the fabric, you notice from the if you recall the Shearflex picture I had before, the fabric's attached to every other rib on the top, and then the exact opposite on the bottom. So the fabric has to slide during the shear flexing action over the top of the rib, or over those ribs where it's not directly attached. So what do we do to minimize the friction? Well, we smooth that rib, sand it really carefully around the edges of the wood, and then we rub it with wax. The kind of wax we call in North America paraffin wax. I don't know what the name of it would be here, but you buy it like in a houseware section. It's not used for candles. It's used for like sealing jars and things of that sort. What would the name be here? Anyone know? If you're like had a jar of fruit that you're sealing up, you pour this wax on top to provide an airtight seal. Yeah, maybe that kind of wax could be. So someone once asked me on a radio show, well, does your aircraft have wax on its wings like Icarus? And I had to say, well, yeah, actually it does. That's where the wax is. Okay, here's the completed aircraft structure. This is in 1996. This was the team at that time, and you can see what it looks like with the covering off. Later on, we had to put a longer landing gear on because the wingtips were too close to the ground, and there's all sorts of developmental issues. But nonetheless, this essentially is the aircraft. All right, let's look at the beating heart of the aircraft. This is the drivetrain and engine. The engine itself is a 3-cylinder, 2-cycle design from Germany called a Koenig. It's designed for ultralight aircraft. And it produces 24 horsepower. It's been a really sweet engine. This is the drive module. It's a little bit hard to see here. Maybe this drawing is a little better. It goes through 4 stages of sprockets and chains, because we have to get the high rotational RPM of the engine down to the low oscillatory frequencies for the flapping. And it has to be an up and down motion. So again, it terminates into the Scotch yoke. This is the yoke, and these are the slider bearings, and there's 2 posts here, steel posts. So this yoke, this brown thing, is sliding up and down. Here's the crank arm. This crank has a bearing that fits inside of a slot, a long way slot in the Scotch yoke. So as this crank arm goes around, it moves the Scotch yoke up and down. And then the center section of the wing, the center panel is attached to that, and that provides the motion. Essentially, it's the same as what we did with the quarter scale model. Okay, our first tests were in 1996, and immediately we saw we're not just going to take off and fly. There was like numerous little structural issues, and the undercarriage was too short, and so forth. But that's what you have to do. That's what testing is for. That's why it's called testing. Registration. This is registered with Transport Canada. They've been great about this, and we had to have a builder's plaque put in it. You can see it's Well, Ornithopter No.1, okay, serial number 0001, right over here. You know, we just had to sort of think of what would be appropriate to put on the plaque. And we have what's called a Special Certificate of Airworthiness from Transport Canada, which allows us to fly above a runway, but we can't go off and do a circuit, even if we could, because we're in a populated area. We're doing our testing on the Bombardier runway at Downsview, Ontario, just a little south of my office at the Institute for Aerospace Studies. It was very convenient. And we're based out of the Toronto Aerospace Museum. They have a hangar there. And of course, what they hope is that when we're done, we'll leave the aircraft there so they can add it to their collection. Here's the Ornithopter Assembly. Just earlier today at the Science Museum, I saw the construction of a Spitfire, and it showed about, I'd say about eight guys who were like bent over like this with the wing on their backs, and they're like moving up and down while somebody else is trying to fit the bolts in. Well, it's almost like that. I have students of various size ranges, some nice tall students here who are able to get up here and put the bolts in, the pivot bolts, and some very short little students who can get inside the cockpit and do wiring or other types of repairs like that. But being an ornithopter with flapping wings means that it's very disassemblable, which has been really convenient for transportation and storage. This picture I really like because it's so typical of experimental aircraft. You know, a bunch of engineers or technicians hovered around an aircraft. Part of the aircraft is off, you know, for access to what's inside. There's the thing they're standing on here, you know, fiddling around. You see that all throughout aviation history. And sure enough, we see that with this particular aircraft. Notice our registration number, CGPTR. Transport Canada reserved PTR for us. Now, that's an interesting story. Because up until about 5 years before we started construction on this, Transport Canada had a category for ornithopters. They tried to cover everything, you know, helicopters and fixed-wing airplanes and what have you. And they also, just for completeness, had ornithopters. Finally, they said, this is nuts. Nobody's ever going to build an ornithopter. So let's remove that category. Sure enough, I call. And the guy said, I know it. I know it. I know as soon as we got rid of that category, somebody had called building an ornithopter. Hey, so you know that's. But they've been really great. They've been a great help to us. If you're going to build a unique experimental aircraft, talk to them or talk to your certifying agency, the CAA, before you start building the thing. If you show up with a finished aircraft and say, "Okay, give me a certification," you're going to have trouble. If you get them in the loop right from the beginning, life is so much easier. Okay, to fly this thing, since we don't have direct roll control, it's the all-roll coupling, we don't have ailerons, we have to get up really quite early so that the winds aren't too high. So here we are at dawn's early light, rosy fingers of dawn. Everybody's stumbling out onto the field, half asleep. And, you know, a lot of them are students. They probably didn't even bother going to bed. But they're there. Here's our pilot, Jack Sanderson. Did any of you ever see a movie called Fly Away Home about these geese that were trained to fly behind an airplane? He did Anna Paquin was one of the stars in the film, and Jack's a wee little guy, and he filled in for Anna Paquin for the flying scenes. And he's a superb pilot of ultralight and general aviation aircraft, and we're so delighted to have him on the team because he is able to wring every ounce of performance and potential out of this aircraft. Okay, now, typically, the aircraft wound up heavier than the design. We were so sure we were building a 600-pound aircraft. You know, we just went through the calculations and checked everything. But again, starting from the Wright brothers on, aircraft have always been heavier than you've estimated. I should have not let that get past me because the aircraft now is 760 pounds all up. So we needed help. An ornithopter wing is not happy flying at off-design conditions. It has to be essentially flying at its design condition, at least this particular type of wing. It struggles if you're in an off-design condition. It isn't like I could put more power into it. If I flapped it faster, I'd have structural problems. And it isn't like, you know, with a propeller-driven airplane, you just put a bigger engine and a bigger propeller and then you take care of business. But no, We're stuck with this wing. We have to work with it. So we had to give the Ornithopter some help with its lift. And here's a model that's in my wind tunnel at the Institute, where we're investigating putting on a wing of this sort. Interestingly enough, that also has a Selig airfoil, a different one, of course. So here's the aircraft with the subwing. And that helped a lot. That was something we had to do basically to get off the ground. Now, some people have criticized this, saying, well, it's not a pure ornithopter anymore. Well, okay, we could just say, well, that's it. We're going to go home. Or we could put this wing on and learn something. So that's what we had decided to do. Besides that, when it comes to what's a pure ornithopter and what isn't, I'm going to leave that to the historians. I got other things to think about. Here's one of our teams. This is a team from this year. That old guy in the middle is me. And we've had, throughout the years, a remarkable group of young men and women who have been motivated by this project. You can visit our website and you can see all the teams that we've had. The students, well, people ask me, what's the practical application of the ornithopter? Well, there's no overt practical application. We're just doing something just for the beauty of it. But from an academic standpoint, it's first of all been a student magnet. The students have been attracted to the project because where else can you go out on a runway and make a little bit of history? And the other thing, too, is that it's been intellectually stimulating. Many theses, fourth-year theses, master's theses, PhD theses have evolved from this, all on aeroelastic modeling, on unsteady aerodynamics, on topics pertaining to bird flight, topics pertaining to micro-air vehicles. This year, for example, there will be 4 papers published, 3 in the Journal of Aircraft and 1 in the Canadian Aeronautics and Space Journal, all pertaining to spin-off research from this project here. This is all for like small-scale flapping, but again, you know, what we learned from this led us to other work. 4 of these guys are actually from France. They had like a student exchange program, so they came over and spent time with us. Now, another problem is that this Shearflex wing has very poor static thrust. It takes forever for it to get up to speed because at the very beginning, at the low advance ratios of the flapping, the flow is primarily stalled. It does have some leading edge suction, enough to get us going, and then finally about halfway down the runway, it's scooting close to takeoff speed. Well, that doesn't leave us much room to do anything. So what we did was to incorporate a small jet engine from Advanced Micro Turbines in the Netherlands. This is their Olympia jet. So yeah, okay, talk about telling people what you do. I have a jet-propelled flapping wing airplane. Imagine reaction to that, right? But it's a sweet little power unit. It worked very well for us, and we had a lot of good cooperation from AMT. Here we are, preparations for testing again at the hangar. This was on the day of the flight. We have this truck. One of my former students, who's an engineer on the project, has this transporter truck that's great. Everybody piles into the back of it with their cameras and so forth, and it acts as a chase vehicle for the aircraft. All right, I'm going to show the flight from last year. Now, I want to emphasize 2 things to you before I show it. When Jack got off the ground, he didn't cut the jet. The idea was to get off the ground and cut the jet, but he kept the jet on for the 14 seconds it was off the ground. So this isn't a pure flapping flight, but the wing thrust is a lot more than the jet thrust. Okay, so that it was primarily flying from flapping thrust. But nonetheless, you know, we still had the jet going. Second of all, near the end of the video, you'll see the aircraft kind of wobbling. What had happened was that this was the first time the aircraft experienced steady in-flight loads. And on the left wing, one of the trailing edge strips had localized buckling, which jammed up the shear flexing action. And when you jam that up, all of a sudden you're like losing thrust and losing lift, which clearly shows the role that the shear flexing is doing. Why didn't it happen on the right wing? Actually, a previous mishap caused us to rebuild the wing with a somewhat stronger trailing edge. But we didn't change the left wing because up to that point, there'd been no problem. We had no reason really to change it. But now we have. But that's the things to look for. Nonetheless, we were in the air for 14 seconds. Now, just to conclude things, our expertise on large-scale flapping flight led us to obtain a contract from DARPA on a micro-air vehicle called the Mentor. This is a vehicle that uses the principle of clap fling as discovered by Torkel Weiss-Fol at Cambridge University in the 1970s. So it really does work, and it's the way that insects, many insects fly, as well as certain hummingbirds. And you know clap fling from when you startle a pigeon. All of a sudden you hear bang, 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 bang from the wings. That's sort of like nature's afterburner. It gets you off fast. It's very, very energy intensive, but for quail or pigeons who are trying to take off in a hurry, that works well. Here I'll show you what clap fling looks like. This is our little rig we had in our setup on a workbench. See how the wings peel together? It's a way to get super circulation, super bound circulation on the wings, because when they're together, there is no CUDA condition. So the leading edge can spread out before the trailing edge separates, and you then wind up with a set of wings with super circulation and very high lift. Weiss-Fol had calculated the average lift coefficients of these tiny little wasps called Incarciformosa. He was getting like lift coefficients of like 6. Like, okay, what's going on here? These things are at a Reynolds number where to them the air seemed like molasses, and it was the clap fling phenomenon that did it. Okay, now if you want to see more of these videos and the list of the various publications in the Aeronautical Journal, the Journal of Aircraft, and so forth, you can see that on our website. It's ornithopter.ca, CA for Canada.
Well, James, thank you very much indeed for that presentation. I think 14 seconds, probably a year, a second of engineering and science to support that. I don't think any of us should underestimate what went into that flight. The melding of engineering, of science, of physics, of pure bloody mindedness to overcome the problems, and to some extent to overcome the, as you say, the publicity, which is the negative one of these grainy films and the mad inventors. All of that, and I think the youngsters are attracted to it, like you, should feel proud of what you've achieved. And for coming and sharing that with us tonight, very many thanks indeed. I wish you a very successful